In this video, we will derive the overall energy balance around a system potato, the general energy balance. The system potato is any system boundary that surrounds the system of interest that we are going to investigate. And through these system boundaries, we will have flow, heat, and work interactions. Now, fluids can come in and go out through the system boundary. So I will call m dot in, and I will have another fluid exchange port that will allow the fluid to leave the system boundary. These boundaries will represent the flow exchanges, the mass exchanges through the boundaries. The system can exchange heat through a diathermal wall, a wall that can conduct heat. Okay, so we will have heat exchange through the system boundary. We'll call Q dot, and that represents that it is a heat transfer rate. This dot represents that it is the mass flow rate. And the system exchanges work through mechanical motion, like an impeller we use in a mixed flow reactor, or the system exchanges work with its environment through surface boundary movement. So we have a piston, and the movement of this piston exchanges work against the environmental pressure. Mass flow, heat flow, and work flow. This is identified as shaft work. This is the surface boundary work. And we are going to have another term for the work, which we call the flow work. But let's first derive the overall energy balance and then define the work terms. The overall energy balance is the general energy balance, also called the first law of thermodynamics, is in line with the general balance equations. In other words, time rate of change of the conserved quantity within the system boundary is equal to the net rate with which the conserved quantity enters through the system boundary minus the net rate at which the conserved quantity leaves through the system boundary. So we are going to have a time rate of change of term. This time it is going to be the total energy, but before I substitute the total energy here, I would like to define what I understand from that total energy above. I will define energy as E. This energy, as I am going to specify, is going to contain several terms. The first term will be the internal energy. The internal energy is defined as the energy stored in the molecular bonds and molecular motions. The internal energy, as we are going to use in this derivation, we'll have the energy that are stored in vibrational, rotational, and translational motion of the molecules, and also in the chemical bonds of the molecules. That is the internal energy. Plus, it is going to be the kinetic energy. But this time, the kinetic energy is going to be the kinetic energy of the macroscopic domain. In other words, the kinetic energy of the fluid package plus the potential energy. Again, it will be the potential energy of the whole fluid package plus any kind of electromagnetic energy that our system may possess, plus any kind of nuclear energy that our system possesses, and anything else you can think of. Now, for the problems of the interest to us, we rarely resort to including situations that have kinetic energy, potential energy, electromagnetic energy, and nuclear energy interactions. And we are limited with the situations that internal energy interactions are dominant. As a result, my conserved quantity is going to be limited to the internal energy as far as the energy stored within the molecules are concerned. Now we have internal energy, time rate of change of internal energy within the system boundaries. The system potato is equal to the net rate that energy enters through the system boundaries. All right, we have these mass flows coming in and going out. They bring in their own internal energies. This internal energy refers to the internal energy of whatever is residing within the system boundaries. But then these streams will bring in their own internal energies along with them as well. So we're going to sum over all streams that come in through the system boundaries. Here we have only one, but we don't have to have one stream. We can have infinitely many streams that are crossing through our system boundaries. So we're going to use the summation term to have the most general form. This is the mass flow rate. When we put a hat on top of the internal energy term, it is going to imply that this is energy per unit mass. And when we put a dot over the mass flow rate, this is going to indicate that this is mass per unit time. And when we multiply them, we get masses cancel. The unit of this term, or this term, has the unit of energy per unit time energy per unit time, and this term has the unit of energy per unit time. So our balance equation is dimensionally consistent. Okay? This derivation is going to have a lot of information. Bear with me but at the end we will get a neat, clear answer in a single attempt. So this term, summation over all incoming streams that bring in their internal energies, minus all the streams that leave the system boundaries m dot I u I hat. This is not the only interaction that we have. Now, if this fluid element, if it is going to be able to force itself through the system boundaries, it has to push the fluid element that is ahead of it. All right? So this fluid element has to force itself into the system boundaries, and the only way that this fluid element can force itself through the system boundaries is through the PV work. All right? Unless this fluid element is at a greater pressure than the contents of the system boundary, the flow cannot go in. So I have to take that into consideration. Okay? I will add the PV work that are pertinent for all the incoming streams, m dot I times P times V hat I. This is the specific volume per unit mass. And of course, in order for this fluid element to leave the system boundary, it has to push its way out, and in order to be able to push its way out, its pressure here should be greater than the pressure at the outlet. Therefore, I have to write an equivalent term for the outgoing stream. All right, so those two terms are called the flow work terms. We need to take other work terms into consideration. What else we have? We have shaft work. This is the shaft work. What else do we have? We have surface boundary work. Surface boundary work is a direct consequence of the Newton's law. Work is force times the displacement. We're going to have this term as minus P times dV over dt. This is the surface boundary work. Then we have the heat interaction plus Q dot. The overall energy balance can be rearranged and simplified as follows. Now let's first bring the surface boundary work term, P dV over dt, to the other side of the equation, where we also have another d over dt term. We have du d over dt, du over dt, let me not go very fast, plus P dV over dt. Okay, I grouped similar terms together. And I'm now going to group similar terms together here. Is going to be equal to summation of incoming streams with their mass flow rates UI plus PIVI minus summation of outgoing streams m dot I UI plus PIVI plus shaft work plus Q dot. Now we have a specific term for U plus PV. We call it H, enthalpy, HI. HI. Remember that our system potato represents a reactor that interacts with its environment through mass exchange, flow streams, through surface boundary movements. Our reactor can expand and contract. An expanding and contracting reactor example is a very good example is the car engine. That our reactor can have an impeller that rotates. A good everyday example of your impeller rotating in a reactor is your dishwasher and its impeller. All right. And of course, heat exchange. That when you take in the water into your dishwasher, you have to heat it up. There has to be a heat input to your dishwashing reactor. All right, so I have to do one more approximation till we arrive at the final answer. The approximation is going to take our reactor system at constant pressure. Under constant pressure, d over dt U plus PV can be combined. Because this is constant, this can enter into the derivative sign. I can collect them in a common parentheses. And remember, I called this H. All right? But I can only do that under constant pressure conditions. All right? Under constant pressure conditions, my general energy balance becomes dH over dt to be equal to summation of all the streams that are coming into the reactor, m dot I, HI, minus all the streams that are going out, m dot I, HI. They're different streams. They may have the same index, but they're different streams. Shaft work. The work that we need to do to turn the impeller. Turn the impeller of your dishwasher. You need electricity. You have to do work. You have to take that into consideration. All right? Plus Q. This is the general energy balance over a system potato. Now, I would like to emphasize a few things. Now this H hat, it is the specific enthalpy per unit mass of the streams, flowing streams, but this H is the enthalpy of the content of the reactor. Okay, this is the enthalpy of the content of the reactor. Now, if we follow through the dishwasher example, that in your dishwasher, you take in tap water. You take in tap water, which is around 15 degrees Celsius. The enthalpy that is coming in is the enthalpy of the tap water. This enthalpy here that represents the enthalpy of the reactor content is the enthalpy of the water that is doing the dishwashing. That water contains detergents, that water contains the contaminations that are removed from your dishes, and that water is at temperatures close to 50 degrees Celsius, depending upon your choice of the temperature of using the dishwasher. And the outlet stream, of course, is going to have its own enthalpy. By the time you discard your dishwater out of your dishwasher, that it will get cooled down, that it will be at a temperature that might be different from the content temperature. So be careful about assigning your enthalpies. And shaft work is the work that our impellers do. Q is the heat that we provide to heat the contents of our reactor. And this is the general form of the energy balance. In this video, we are going to differentiate the reaction heat from the heat transfer. We will do this on a hypothetical reaction of A and B producing P and R with their corresponding stoichiometric coefficients of lowercase a, b, p, and r. The analysis we are going to conduct will be around a flow reactor, but this is going to be a general flow reactor. We are not going to identify whether it is a CSTR or a plug flow reactor. Therefore, it is a generic rectangular box representing our reactor. Here we are going to use the term conversion. Conversion is defined as the difference between the concentration at the inlet or in the beginning minus concentration at the exit or at the end of the reaction divided by Ca0. What fraction of the reactant is being converted during the reaction is represented by the term conversion, and X is the symbol that we are going to use. Now, first we are going to simplify this reaction by rendering one of the reactants with unity stoichiometry, all right? And that unity stoichiometry for component A allows us to define the conversion term, and this conversion term is going to simplify a complex domain with many different parameters to one single parameter that is called conversion, and we are going to here evolve the energy balance in its most general form to an energy balance that incorporates a chemical reaction. And before we do that, we have to have a rigorous material balance analysis in our hands. In order to be able to get this rigorous analysis, we have to have a stoichiometric table. In the stoichiometric table, we will have species that we will have their incoming rates. We will have the change that has occurred within the reactor, and we will have the outgoing rates. So our species are A, B, P, and R. Their incoming rate is FA in, FB in. Let's have P and R also at the inlet streams. We may have a recycle reactor where we couldn't purify the product and some P and R leaks in to the incoming stream, for example. How much change has occurred? Now, FA in okay, the conversion that was already written was written for a batch reactor. For flow reactors, we define conversion in terms of molar flow rates, FA in and FA. So the change that we have for species A is going to be FA in times X. And at the outlet, we have FA. And FA is equal to FA in times 1 minus X. Okay. Now the change in B is going to be proportional to the stoichiometry of B to A. If A has FA in times X moles converted, then B should have, of course this is consumed, so I have to put the minus sign. If A has so much being consumed, then B should have FB, FA in times X, the minus in front, times the stoichiometry B over A. Right? I divide by the stoichiometry of A and multiply by B. So this is going to be FB in minus B over A, FA in times X. With the same logic, we have FA in times X times this time P over A, and FA in X times R over A. Similarly, remember, just notice that I didn't put minus sign because these are being consumed, they're depleted, and these are being produced that they don't have to have a minus sign. So this is FP in plus P over A times FA in times X, and this is FR in plus R over A times FA in times X. Remember, notice that we all have FA in times X terms here. What I will do is, just like I have taken this into FA in parentheses, I will take this one into also FA in parentheses. And I'm going to have FP in over FA in minus B over A X. And I will call this term as theta B, feed stoichiometric ratio of B to A. And when I do the same for the others, I will have FA in theta P plus P over A times X. And we have FA in times theta R plus R over A times X. This is our stoichiometric table. Now we had two terms in the energy balance, summation of the incoming streams and outgoing streams. Now what I will do, I will convert them to their corresponding mole basis equivalents. And in order to convert them to their mole basis equivalents, I have to do a little trick. Instead of mass flow rate, I will divide it by its molecular weight, and it will immediately become Fi, molar flux of the incoming stream. And of course, in order to have dimensional consistency, my enthalpy should have an underscore. This one is enthalpy per unit mass. This is enthalpy per unit mole, molar enthalpy. Similar here. All right. Outgoing stream, Fi, Hi, with an underscore. So I'm going to substitute Fa terms here for the incoming stream, Fi terms here for the outgoing streams. Okay? So my flow reactor is a black box. It is operating at steady state. As a result, my time-dependent term in the energy balance doesn't have to enter into consideration. 0 is equal to, let us see what we can write for the incoming stream. Fa in Ha in plus Fb in Hb in plus Fr in or Fp in Hp in plus Fr in Hr in. So this is the incoming stream. For the outgoing stream, Fa out is this, Fa in times 1 minus x. Fa in times 1 minus x times Ha out. Fb out Yes, it is FA in times theta B minus B over X. FA in times theta B minus B over A times X. I have to put a minus sign, put a square bracket here, plus FP out. It is FA in times theta P plus P over A times X plus FR. FA in times theta R plus R over A times X. What other terms do we have? We have Q, we have shaft work. All right, so this is our energy balance. Now I'm going to group similar terms together. Everything has FA in, HA in, FA in, HA out. 0 is equal to FA in. Let me get a square bracket. HA in minus HA out. Then I have FB in or in this global FA in parentheses, I can write plus theta B times, so FA in, HA in minus HA out plus, now instead of FB in, since I have FA in the parentheses, I write theta B, HB in minus HB out. It has taken care of I have to have HB out here. I missed those terms. HP out. And of course, HR out. Okay? Plus theta P HP in minus HP out plus theta R HR in minus HR out. So this has taken care of the first terms, FA in, and these first terms, one, the term with theta, the term with theta, the term with theta. Now I have to take care of the second terms, the terms that have X. All right? So I'm going to have, I have a minus, minus, plus. Plus FA in times X. I have HA out plus B over A times HB out minus, it is plus, it's going to make it minus, P over A times HP out minus R over A times H R out. Now this term is minus delta H reaction. So when I sum this up in concise form, I obtain 0 equals to FA in summation of all the terms of theta I summation over all the species theta I of H in minus H out plus FA in times X times minus delta H reaction plus heat plus shaft work. All right, this is the steady state energy balance for a reactor. This is the reaction heat. This is the heat transfer. This is the reaction heat. This is the heat transfer. Do not confuse those two terms.